All right, subscribers, welcome back to another episode of Science with Surback. Today, what we're going to be talking about is AP Chemistry Section 17.5. And before we get into the details of these notes, I just want to outline a couple of objectives that I want you to be able to accomplish by the end of this video. So, objective number 1, predict whether a precipitate will form when two solutions are mixed together given appropriate KSP values. Objective 2, explain the effect of pH on solubility equilibrium involving basic or acidic ions. Objective number 3, write the equilibrium equation when a metal ion and a Lewis base react to form a metal complex ion. And then objective number 4, describe how complex formation can affect the solubility of a slightly soluble salt. So, we move into factors that affect solubility. And so, there are 4 different factors. And the first factor that affects solubility is the presence of a common ion. So we saw the effect of a common ion on the pH of an acid or base. Well, that common ion can also affect the solubility. The second factor that can affect solubility is the pH of the solution. Remember, the pH deals with the hydronium or hydroxide concentration, and putting those types of ions, or talking about that, will again affect that solubility. The third factor that affects solubility is the presence of complexing agents. So what we mean by complex agents, if you think back to those metal ion complexes, that is exactly what we're talking about here in point number 3. And then the fourth factor that can affect the solubility is going to be that amphotericism. And now that is related to the effects of both pH and complexing agents. And remember, something that's amphoteric, it can either act as an acid or base, has the capability to do either of those. And now point number 4 is really just an extension of points 2 and 3. So let's go in detail into each of these 4 factors, talk about them. We'll do a couple examples with some of them, and then that will conclude section 17.5. So we start out here with the first factor that affects solubility, and that is that of the common ion effect. So, for the common ion effect, the solubility of a slightly soluble salt is decreased when a common ion is added. So when we add that ion, that common ion, the solubility is going to be decreased for that ionic substance. The best way to see this is through an example. So we have calcium fluoride here. That when dissolved breaks down to calcium 2+ ions and those 2 F- or fluoride ions. And so if more F- is added via something like sodium fluoride, the equilibrium shifts to the left to offset the increase of that common ion. All right, so what happens here if we add that F-? We shift the equilibrium to the left here, and what that really means is that the solubility of calcium fluoride decreases. All right, so we can actually see the effect of a common ion on solubility via a problem. So what we're going to do here, we're going to shift gears a little bit, and we're going to actually go through a common ion problem and see what happens to the solubility of a certain substance. So we want to calculate the molar solubility of calcium fluoride in number 1 in our first solution of 0.010 molar calcium nitrate. So the first thing that I like to give is that roadmap, that picture, which is in our chemical reaction. So we have calcium fluoride, which we've seen this example before. Calcium fluoride as a solid gets dissolved in that water and comes to equilibrium where it forms calcium 2 plus ions and 2 fluoride ions. Now, before, what we would do is we would produce that ice chart. So to find our KSP, we're going to produce that ice chart here. But before we insert the initial values, what I want to do is this. We now have 0.010 molar of calcium nitrate. So calcium nitrate, down below here, calcium nitrate, CaNO3 2. In solution, what happens to that is that it breaks down to calcium 2 plus and it breaks down to 2 NO3 minus ions. Now, we have 0.010 molar calcium nitrate. So because we have 0.010 molar, this means that because there's a 1-to-1 ratio between calcium nitrate and calcium, this means that there is already an initial concentration of 0.010 molar. So what we do for just calcium, this is just calcium ions, for that initial value, we can place 0.010 molar. Now, there was no fluoride initially, so we have to put a value of 0. Now, we add in our value of x. There is some amount of x gained, and then we have to put 2x here for the fluoride because there is that coefficient out in front. So at equilibrium, what we end up getting is 0.010 plus x and then 2x. So now what we have to do is plug it back into our equilibrium or our solubility expression. So in this case here, our KSP is equal to calcium 2 plus times the concentration of F minus, but remember, we need to square that term because of that coefficient. So what we are going to do is this. We are going to look up the value for KSP via the textbook, and we are going to solve for what is that molar solubility of our calcium fluoride. So let me grab another sheet of paper. I don't want to squeeze this into a place where it shouldn't be, so I will do that. All right, so what I'm going to do with my other sheet of paper here is I'm just going to rewrite that equilibrium constant expression. So we said KSP is equal to the concentration of calcium 2 plus ions times the F minus, the fluoride ions, squared because of that coefficient. And then we have this. Now, we are dealing with KSP, which it's nice for us because in Appendix D, what you'll get is this. You'll get this particular chart. So if you look up calcium fluoride, let's see, right there, calcium fluoride has a KSP of 3.9 times 10 to the negative 11th. So instead of KSP, I'm actually going to put this value down. I'm going to put 3.9 times 10 to the negative 11th. Now, what we just established from our ice chart was this. Calcium, the calcium 2 plus ions at equilibrium is 0.01 plus x. So what I do here is I insert this as 0.010 plus x, and then I multiply this by what my F minus was, which if we bring this sheet back over at equilibrium, this F minus was 2x. So I insert the value for 2x and I have to square it. Now, if you can forecast out, this business right here is going to lead to the quadratic formula. And so it's actually going to lead to an x to the third power, even more complicated. What we have to do is this. We have to see if we can't assume that this is going to be so small that it doesn't matter. So again, we have to write out any assumption that we use. And this time, it's going to be KSP times 100 needs to be much, much smaller than our original concentration, in this case of our calcium 2+ ions. So our KSP is 3.9 times 10 to the negative 11th times 100 needs to be much smaller than this 0.010 molar. So we grab out our calculator and we calculate this out. So we take 3.9 times 10 to the negative 11th times 100, and we obtain a value of 3.9 times 10 to the negative 9th. Now, this is much, much smaller than 0.010. So we can assume this we can say 0.010 plus x is essentially equivalent to 0.010. So what we do to solve this problem now is we get rid of this plus x. So I'm just going to rewrite this as 3.9 times 10 to the negative 11th equals the concentration, which is 0.010, not plus x because we made that assumption, times this. Now I'm going to go ahead and calculate this. This is 2 squared is 4, and then x squared is x squared. So now what we have is this. What I'm going to do is I'm going to write down 3.9 times 10 to the negative 11th equals, and here's where I'm going to grab my calculator, equals this. I'm going to take it out of scientific notation. 0.01 times 4, I get a value of 0.04, and this would become 0.04 x squared. Now, I have to get x by itself, so I divide both sides by 0.04. So in my calculator, what I do is this. I take 3.9 times 10 to the negative 11th divided by 0.04. And I obtain a value of 9.75 times 10 to the negative 10th. And this is set equal to x squared. So to get rid of x squared, all I need to do is take the square root of both sides. And so because my last answer is still inserted in the calculator, I can hit second, get that square root button, and then I can just insert that answer. And now this answer gives me 3.1, I do some rounding, 3.1 times 10 to the negative 5th. So 3.1 times 10 to the negative 5th equals x. Well, if you remember way back when we started this problem, it said calculate the molar solubility. And because we found x to be this answer, 3.1 times 10 to the negative 5th becomes our molar solubility, the number of moles divided by liters. So our answer here, when we go through this process, is this. 3.1 times 10 to the negative fifth moles per liter equals our solubility of calcium fluoride, and that calcium fluoride had that common ion. So we have to remember that. Now, moles over liters can also be expressed as molarity, but this becomes our final answer into our problem. Now what we do is this, a very similar fashion. Hopefully it won't take as long, but we now have a common ion. In problem number 2, we have the same setup, but we have sodium fluoride. So what I'm going to do to start this problem is just rewrite my equilibrium expression just like I had up here. Oop. Calcium fluoride's not aqueous set, it's solid. Goes to equilibrium, forms our calcium 2 plus ions, and forms 2 F minus or fluoride ions. Again, we set up our ice chart. Now, our initial values for calcium, this time there was no calcium there, so we can say, hey, there's 0. Now, what happens to our sodium fluoride? Very similar thing that happened up here. It breaks down to sodium 1 plus and fluoride 1 minus. So because this is that 1-to-1 ratio, we can assume that initially there was 0.01 molar initial concentration from that common ion. Now, what happens here is over time, we will gain some amount X from our calcium, and we will gain some amount 2X from our fluoride. So at equilibrium, we end up with X in 0.010 plus 2X. So now we go back and we have our KSP, which is the same KSP. So we have KSP equals the concentration of our calcium 2 plus ions times our fluoride ions, but we have to remember to square that because of that coefficient. So what we end up doing is this. We insert our values back into our KSP expression. And so what we have is this. Remember, KSP, we're still dealing with calcium fluoride, so it's still the same KSP value. And if you remember from our previous problem here, KSP, in the back of the book, we found it to be 3.9 times 10 to the negative 11th equals our calcium, which is X, times our fluoride, which is 0.010 plus 2X, and we have to square that. Now, it gets pretty ugly unless we make an assumption. So our assumption, once again, we have to write this out because we are doing this. We're assuming our KSP times 100. So 3.9 times 10 to the negative 11th times 100 has to be much, much smaller than our original value for our fluoride, which was 0.010. Now, we multiplied that out from our previous problem, so 3.1 times 10 to the negative 11th is, how about times 10 to the negative 9th? Nonetheless, it's still much smaller than we can assume that we have this 0.010 plus 2x is virtually equal to 0.010. So now what we have is this 3.9 times 10 to the negative 11th equals x times 0.010, but we still need to square this. So what I'm going to do is solve for x. I'm running out of space, and I can solve for the x. So what you do to solve for x is you would take 3.9 times 10 to the negative 11th, and you would divide it by 0.010 squared, and you would obtain your answer. Now, our value for this of x is 3.9. 3.9 times 10 to the negative 7th. So what that means, because we have x equal to that, our molar solubility also becomes that same value that we have for x. So the molar solubility, again, is moles per liter of calcium fluoride, and that's because it had that common ion of sodium fluoride, or had that fluoride ion to begin with. So you can see the effect that a common ion has on the solubility of some substance. Very similar calculation to what we have been doing, and now what we can shift our focus to, that's actually our only math problem here associated with this. We can now focus our attention on those other three factors. So we start out this particular section talking about the solubility and pH. So we have three general statements that we utilize with the solubility and pH. The first of these statements is this: the solubility of a slightly soluble salts containing basic ions increases as pH decreases. The second general statement is the more basic the anion is, the greater the effect pH has. And then the third general statement is the solubility of salts with anions of negligible basicity include Cl-, Br-, I-, and NO3-, or chloride, bromide, iodide, and nitrate. All right, so the best way to see this is through some examples. So we start out here with the solubility of magnesium hydroxide, and it breaks into what you see here. And so we have a couple things. If we have our OH-, our hydroxide, removed, then the equilibrium shifts towards the right, and magnesium hydroxide, or more magnesium hydroxide, dissolves. So OH-, if we remove OH-, we're going to make the solution more acidic, and we can remove OH- or hydroxide by adding a strong acid. So that OH- here, if we add a strong acid, it's very similar to a titration. What happened as we added a strong acid or strong base, we have to go through that neutralization reaction, and that's what's happening here. Now, the big overall statement for an example like magnesium hydroxide is that as the pH decreases, the hydronium ion concentration increases, and the solubility of magnesium hydroxide increases. So that last point is probably really important here. Decrease the pH, we increase the solubility of a substance like magnesium hydroxide. Now, on the flip side, we have lead to fluoride down below here, and we're going to make some general statements like we did above. So with our lead to fluoride, if the F- is removed, the fluoride ions, then the equilibrium shifts towards the right, and lead to fluoride dissolves. So again, these fluoride ions can be removed by adding a strong acid. So we get to this, probably the most important statement here is this: as pH decreases, the hydronium ion concentration increases, and the solubility of lead 2 fluoride increases. All right, so now we've looked at 2 of those 4 factors that factor into what happens to the solubility of a substance, and now we can get into the third, which the third is talking about complex ions and what their effect is on solubility. So, our complex ions, we have a general statement here. In general, the solubility of metal salts increase in the presence of a suitable Lewis base, which includes things like ammonia, the cyanide ion, or hydroxide. Okay, so the best way, again, to see this particular example is through an actual equation. So we have the solubility here of our silver chloride, and everything is written out here. And now we start out with this. The solubility is greatly increased if ammonia is added. And this has to result from the formation of silver ammonia 2+ metal complex. So if we add ammonia by somehow incorporating this silver ammonia complex, remember the metal complex, we can get the solubility of silver chloride to greatly increase. So what we need to look at is, well, how exactly do we get this silver ammonia complex? And so what happens here is that we have Ag+ ions react with ammonia, and it comes to this equilibria, and it forms this. It forms our complex that we need to add ammonia and greatly increase this particular solubility of silver chloride. Now, these are a couple of things. Number one, this AgNH3 2+ is a metal ion complex, and the NH3 is our attached metal ligand. And so what we have to do is this. We are going to do a little bit different here. And I forgot my subscript. That's really important. Anyways, what we have to do here is we go through this formation of this formation constant called Kf. So we have this, the formation constant, which we call Kf. Now Kf is going to have our metal ion complex, so this AgNH3 divided by our Ag1+ times NH3 squared. Now, what happens from here is we have to incorporate all of this business of adding in this metal ion complex into our overall equation. So what happens is this. Our overall reaction is as follows. We get our silver chloride as a solid to react with ammonia to form at equilibrium our metal ion complex and our Cl-. So let me write that equation down. So there's that overall equation, and I want to make one last point on this particular factor. By Le Chatelier's principle, the forward reaction by dissolving the silver chloride going left to right is favored since Ag plus has been removed from solution. So there is that last point here. Now, it's been removed from the solution. That's because essentially we added these equations together to give us this overall reaction. So all we did was we added this top equation here in purple with the equation we wrote down to form this overall reaction. Now, by doing that, we remove that Ag plus from solution. And so the forward reaction going from left to right is favored. And so we have more of that silver chloride dissolve. Now, this is some complex chemistry, irony a little bit, complex chemistry because we're involving a complex ion. And we are also incorporating this business about Le Chatelier's principle that we learned back in the equilibrium unit. So we have one more thing to talk about here, and that is the amphotericism. So what does the amphoteric substance, which remember, an amphoteric substance is something that can act as either a base or an acid, what does that have an effect on the overall solubility of a substance? So again, I just want to remind you of this. An amphoteric substance is defined as a substance that is either capable of acting as either an acid or a base. So with an amphoteric metal oxide and a hydroxide, those types of substances will dissolve in either a strong acid or strong base. So the best way to see this is really through some examples. So what I'm going to do is I'm going to have some examples where I put this particular amphoteric metal, and then over here I'm going to put the oxide version of this, and over to the far right I'm going to put the hydroxide version of that particular substance. So one example that we have that comes to mind here is our Al3+, our aluminum ion. And so when it forms a aluminum oxide, we get Al2O3, and when it forms a hydroxide, we get AlOH3. And another example that I have here is going to be our chromium 3+. Now, when it forms an oxide, we have Cr2O3. When it forms a hydroxide, we get CrOH3. We also have a substance like zinc, Zn2+. So when it forms an oxide, we get ZnO. And when it forms a hydroxide, we get zinc OH2. And then another example that I have here is tin with that 2+ charge. And so again, we get tin oxide that looks like that. And we get tin hydroxide that would form and look like that. So these are just some of these examples that can either act as a amphoteric substance, just to give you an idea. Now, what this is talking about here is that most of the time that these hydroxides, what they're going to do is they're generally going to form complex ions with several hydroxide ligands attached to the metal. So let me write that down. So this is what we talked about at the beginning, where really this amphoteric has to deal with both pH and the complex ion. So to show you an example of this, to show you an example down below here, we have this. We are going to use aluminum hydroxide. So AlOH3. And aluminum hydroxide is a solid. It's going to form or react with hydroxide, OH minus ions. And what is going to happen is this. It comes to equilibrium and it forms AlOH4, which has a -1 charge. And this right here, what we have formed is that metal ion complex. So that previous page that we talked about metal ion complexes now applies to this scenario, all because aluminum hydroxide can be an amphoteric substance. All right, so there's a lot of in-depth chemistry here that relates to the solubility of a substance and what factors can affect that solubility. So there's just some things to keep in mind as we go through the process of developing our thoughts on solubility and understanding that in a little bit more detail. As always, I hope you have enjoyed this video, and don't be afraid to subscribe.